Hi, my name is Kenny, and this is Lab 4 Circuits for Physics 2212. For an introduction of this lab was designed to build familiarity with circuits and the laws within this setting, such as Ohm's law and resistor capacitor circuits. The experiment itself was building virtual circuits with varying resistors, capacitors, and bulbs, which demonstrates how changes in layout and certain values can create changes throughout the whole system. The results for this experiment were, while two of the models were for demonstration, the last one provided an experimental value for RC that matched our computed value. Some fundamental properties for this lab include Ohm's law, loop rule, node rule, and an RC formula that's specific for this lab that allows us to kind of work out some things and find an RC value later on. Within the actual experiment itself, for our first step, we built the circuit provided and recorded outcomes of different instances for use in some later calculations. And some questions I've answered here included, because the current equals the voltage times the resistance, which leads us to 0.02 amps. My prediction for the current was correct. As well as this, the 0.02 amps remains the same forwards and backwards when reversing the ammeter. And when replacing an ammeter with the voltmeter displays 3 volts and the ammeter displays 0 amps because the loop is broken and the voltmeter is picking up the electrical difference between the two sides. Using the loop rule, the sum of all the potential differences should equal 0, and we can see that by dividing each path and adding all of these up, which we were able to get 0, and you can see that in the chart here. And the ammeter doesn't change when adding the voltmeter to the loop because the voltmeter has infinite resistance. If an ammeter is connected in parallel to the 100 ohm resistor, both of the ammeters will display 0.06 amps. And here are some of the resistances that I found throughout the circuit. And then for the second portion of the lab, with the RC circuit, we have various components that we used here. And when the bulb is connected to this series circuit, it glows brightly and then dims down over time until it stops shining. And then when it's connected to the charged capacitor, it does the same thing. In both of these circuits, the current starts off large and then decreases to 0 over time. And the time for the capacitor to charge or discharge is 7.38 seconds with the 10 ohm bulb and 14.26 seconds with the 20 ohm bulb. For time-dependent voltage, we gathered voltage versus time data from a circuit with a 9-volt battery, a 200 capacitor, and a 30 ohm light bulb. Using this, we determined the RC value experimentally. So here we plotted the natural log of the potential difference over the initial potential difference versus time, which helped us linearize the exponential data we got when we compared voltage and time. And then we use this formula in order to calculate the RC value. The slope of this chart is -1 over RC, which we use to obtain an RC value of 5.988 from the slope value that we got, which was -0.167. And computationally, the RC should equal 6, so this value leads us to a less than 0.2% error. Some what-if questions brought up. If we were doing this lab in real life and we used an actual ammeter instead of a simulated ammeter, an ammeter is designed to have the least amount of resistance possible, and so the virtual ammeter has 0 resistance, but in real life, an ammeter would generate some amount, even if it's small, of electrical resistance, and this would end up creating a lower than expected current. And if we used a real battery to charge a real capacitor with no resistor in the circuit, the virtual model would predict that the capacitor would be charged instantaneously because of assumptions made about no resistance. But in real life, the capacitor would reach full charge fast, but not instantaneously due to the minor amounts of resistance in the battery and the wires. Thank you.